All right, section 9.2, the liquid states. We're going to talk about some liquids. Let's talk about some characteristics of liquids. Liquids exhibit low compressibility. So in a gas, right, you could take that gas and you could squeeze it and squeeze it and squeeze it and squeeze it. And you can change its volume pretty readily and increase the temperature. You can't really do that with a liquid, right? Liquids are not very compressible. They're not rigid. They lack rigidity of a solid. So you can move them around, but you're not going to change their volume. So their volume is fixed, but their shape varies. And they got a relatively high density. So you're talking about around 1 gram per milliliter, whereas a gas is going to be like a tenth of that to a hundredth of that, and something like a solid, like aluminum, is going to be 2 to 3 times that. Liquids are going to exhibit a property called surface tension. Right? So it's the resistance of a liquid to increase its surface area. Because remember, these molecules are attracted to each other. They're intermolecular forces of attraction. So if you're a water molecule and you're on the very, very top here, right, you're not going to be attracted to that air. You're going to want to hang out with your buddies, the other water molecules. And that's going to create some surface tension. And you can do cool things like if you're a water strider insect, you can walk across the water, or you can float a paperclip on that surface tension. Right? Liquids with large intermolecular forces, like water, tend to have very high surface tensions. If you are a swimmer, kind of breaking that surface tension is an active area of research. So if you can break that surface tension, you can go through the water a little bit faster. I think there are some suits they have out there that work to disrupt that. I'll have to check on that. Capillary action is another property of liquids. It's exhibited by polar liquids and involves spontaneous rising of a liquid up in a narrow tube. Right, so if you've got a polar liquid, it can also be attracted to the sides of the tube if you've got a polar tube. Okay? It's going to involve two sets of forces, some that are adhesive, that's the interaction between the liquid and the container, and cohesive forces. Right? So if you've ever had a blood draw, right, this little capillary tube, right, you put it on that drop of blood, and the blood goes up into that tube. Right? That is capillary action. That is one of the ways that trees work. Right? So if you just looked at air pressure alone, there would be a maximum height to trees of about 30 meters, I think. And we got trees that are higher than that are taller than that, because capillary action in the xylem and the phloem allows liquid to be transported up higher than just air pressure alone would allow. So let's take a look at some meniscuses. You have seen all of this. So you've got concave and convex meniscuses. Right? So if I've got a nonpolar liquid like mercury, it's going to form a convex meniscus in a glass tube, whereas polar water is going to form a concave meniscus. So when you go out and you made those readings in your glassware in lab, right, you got out your graduated cylinder, right? If you had water in your graduated cylinder, you were told to read the bottom of the meniscus. If you're taking mercury in your glass cylinder, you're going to need to look at the top of the meniscus. Now, this might be flipped if you have a plastic graduated cylinder. Right, so let's look at what's happening in this glass and water one. So we've got our water molecules that are in here. They're polar, right? Our glass is made up of SiO2, some silicon, and some oxygen. And so it's going to have some polarity to it. So you're going to have some partial positives over here on the silicon, and that's going to attract those oxygens. And you've got some oxygens on the outside of that water, of that silica surface, and those are going to attract the hydrogens in the water. So there's a little bit of a force of attraction between the glass on the right and the water on the left, and that's going to cause that to creep up there. That's just what you're doing with that capillary action, right? So that's how your capillary action is working. Now, if you have plastic, right, plastic which is nonpolar, there's not going to be a force of attraction, just like you've got between this polar surface over here for the mercury and the glass. So the mercury is nonpolar, the glass is polar, right? Oil and water do not mix. There's no force of attraction between the glass and the mercury, and so the meniscus is going to be convex. Right? If you had a plastic tube, which is going to be hydrophobic, right, there's going to be a force of repulsion between the water and the side wall of the tube, and you'll end up with a convex meniscus. Just like you would have with mercury in a glass tube, water in a plastic tube will sometimes have a convex meniscus. Again, you would read the top of a convex meniscus and the bottom of a concave meniscus. Liquids have a property called viscosity, and that's a measure of its resistance to flow. So liquids with a large intermolecular forces or molecular complexity tend to be highly viscous. So something like honey or maple syrup are going to be viscous liquids. Um, Ethylene glycol possesses an unusually high viscosity because it forms hydrogen bonds using its several OH groups, right? So it's going to hydrogen bond here, hydrogen bond here, hydrogen bond here, and we're going to have lots of interactions between one glycerol molecule and another glycerol molecule. It is quantified by what's called the Reynolds number, Re. If you go into the field of acoustics and you want to detect submarines underwater, knowing the viscosity of water at different temperatures or salinities is important. And so you get the Reynolds number. If you are in aerodynamics, knowing you want to build airplanes, knowing the Reynolds number is super important if you're looking at flow across a wing surface or across the lifting body of an airplane. Our structural model for liquids is they have strong intermolecular forces and significant molecular motion. They're free to move. A typical liquid contains a large number of regions with more disorder. So they're not an irregular array like we would see in a crystal or a solid. The number of regions where holes appear is smaller, right? Because they're free to move around, right? Things don't want to have gaps. Their nature is highly dynamic and it's rapidly fluctuating in both regions. So our shape is variable, it's conformal, but our volume is fixed.